Hey, hello everybody who's watching. I'm going to hit you up with your unit vocabulary for our physical behavior of matter unit. So our learning target, as always, I can understand and define the vocabulary of the PBoM unit. All right, so we got 20 words coming your way. Let's check it out. Some of these words I'm sure you're going to recognize. So start paying attention to those ones that repeat. These are going to be common throughout all units this year and definitely on the reference table. So Regents exam, not reference table. So check it out. Temperature. What's temperature? Well, everybody knows it's a number, but chemists know that it's actually a measure of the average kinetic energy of the particles in a sample of matter. How quickly they're moving around is related to the number that the gauge on the temperature probe reads. Okay, it's a measure of average kinetic energy. Now, heat. What is heat? Aren't they heat and temperature the same thing? If it's cold in here, I go and turn up the heat. Well, they're not quite the same thing. In this unit, we study heat as transfer. Heat always transfers from hot to cold, never from cold to hot. As a matter of fact, cold doesn't really exist. Cold is just absence of heat. And so we have to understand that heat transfers from hot to cold all the time, no matter what, period, end of story, regardless of the size of the objects and mass of objects. Kinetic energy. Well, kinetic energy is the energy of motion. And in this graph, we can see potential energy and kinetic energy are related. Okay? The more kinetic energy an object has, the less potential it has. The more potential it has, the less kinetic. Kinetic is what we'll focus on, and kinetic is all about the energy of motion. The faster particles are moving, the more kinetic energy they have. Therefore, the higher temperature they will demonstrate if we were to read it with a thermometer. Now here's potential energy again. This is energy of position. As the car here rides up the side of these mountains, gaining potential, and then it converts it into kinetic as it comes sliding down the other side due to gravity. But in chemistry, potential energy is the energy of position. So where the atoms are related to each other. Solids, they're stuck together, liquids, they're moving past, and gases, they're zipping all over the place. So potential energy comes into heating and cooling curves, which we'll study soon enough. This kinetic molecular theory. Here's a great animation of that basic kinetic molecular theory. It says particles are always moving, solids stuck together even though they're vibrating, liquids roll past as they vibrate, gases are vibrating, moving in straight lines as they bounce off containers, walls, and each other. They transfer their energy. That's what kinetic molecular theory is kind of saying. There's 5 rules we'll study later. These rules are used to describe the behavior of gases. Okay, we don't use kinetic molecular theory really well on liquids and solids, but gases for sure. Next set of 5. Absolute zero. This is absolute zero. That's 300 Kelvin. This is absolute zero. That's 300 Kelvin. At 300 Kelvin, particles are moving. At absolute zero, 0 Kelvin, they are not. So absolute zero is theoretically determined. It's a temperature where all kinetic motion stops. There's 0 heat energy. We have not been able to achieve this yet in laboratory settings, but we're getting pretty darn close. Absolute zero, know it. Normal boiling point. This is a reference table we're going to teach you when we teach about boiling and vapor pressure. Okay, it's table H. The temperature at which a liquid would boil at 1 atmosphere of pressure is its normal boiling point. So what temperature would it normally boil at? Well, normal, we think here, sea level, 1 atmosphere of pressure, and that's how we will determine the temperature at which it boils. 1 atmosphere of pressure, normal boiling point. As we change the pressure, the boiling point is going to change as well, and we'll see that from the graphs. A cooling curve. This is a standard graph of a cooling curve. Starts with high temperature, it's got a flat, a slant, a flat, and it drops down to low temperature. As you can see, it's labeled up. We're going to get good at labeling these things. A cooling curve is a representation of both kinetic and potential energy as the substance is cooled. So it's kind of like a roller coaster. Either it goes down the side of the hill or up the time of the climb, which is what a heating curve is going to do. You'll notice this is exactly the same shape of curve, even though it starts low and goes high. This one's great because it has animations for the particles and phases of matter, which is what the potential energy is in these graphs. So the graphs don't show you the particles, but we're going to learn that the particles are moving in certain patterns during certain times, which tells us about the potential energy. the kinetic energy being related to temperature, it's easy to see that that changes because the graph rises or falls. And there's your definition for heating curve. It's a graph of the temperature versus time as a substance is heated. Evaporation. Evaporation is pretty simple. It's a process, physical process, that changes when the atoms on the surface of a liquid become gas. So that's what that animation was trying to show us, is where the atoms of the liquid are becoming a gas on the surface. That's evaporation. Heat of fusion. This is a special number. We use it when we do our heat calculations, which you can see a curve here with equations written over it, which we will do. But the heat of fusion is the amount of heat needed to completely melt a solid without changing its temperature. Okay, so the heat of fusion is used when we're doing a heat calculation, and the substance that we're talking about is going through the melting or freezing. We use heat of fusion. Heat of vaporization is used at a different time. Instead of melting and freezing, we're going to use the heat of vaporization when we are boiling or condensing. And it's the same concept as the amount of energy used to boil or condense a substance from the liquid or the gas. Okay? No changes in temperature happen there. The heat of reaction is briefly discovered when we talk about table I. It's the amount of energy reactions released or absorbed. It's represented as delta H. The positive and negative sign of it will be what we are paying attention to in the future. We usually figure this out by subtraction difference, the heat of the products minus the heat of the reactants. And this overall shows us the change in heat of the reaction, whether it gets hotter or colder, or releases heat rather, I shouldn't say colder, as it absorbs heat or releases heat during the reaction. Now, the melting and freezing point of substances, well, that is the same temperature. And this is a picture of some gallium melting about body temperature, 85, 86 degrees in the hand. Melting points are the temperature at which substances change from solid to liquid or from liquid to solid. They're the same temperature. Water both freezes and melts at 0 degrees. So, vapor pressure, next fact. Vapor pressure is the amount of pressure that particles are exerting above a liquid. Okay, it's created at the surface, and they push up on the atmosphere. The atmosphere is always pushing down. We've learned not to feel it. Particles do feel it all the time, and so we're going to work with vapor pressure when we study boiling, normal boiling point. A calorimeter. This is a device that's used to measure heat changes. Okay, so while we will be doing calculations for heat changes, getting the data uses a calorimeter, aka calorimetry. It's measurement of heat. Boiling and condensation point. This is, well, that's a boiling point. There's some substance in there, so the water was boiling and left something behind. So let's check out boiling point. It's the temperature at which the substance turns from a liquid to a gas, or from a gas back down into a liquid. They're the same temperature, just like the melting and freezing point are the same temperature. Ideal gases. Well, this is a particle in a box model. It's describing the behavior of a gas particle. Ideal gases are under high temperature, low pressure, so they can move in straight lines without bumping into anybody. And they're usually obeying the typical kinetic molecular theory most closely at this time, which is what we need to have so that our combined gas law equation is going to work. We have to assume that our particles are behaving like an ideal gas to use that equation. The combined gas law combines 3 different laws, Charles' law, Boyle law, Guy-Lussac's law, into one large expression. We're going to study those discrete laws as relationships, but the equation for the combined gas law is what's most important. Now, standard temperature and pressure. This has been messing people up left and right because it's used as an acronym, STP. And so there's your values, reference table A. It's used as a standard of comparison for all gas behaviors, because we got to know how your experiment behaves at 0 Celsius in 1 atmosphere so that an experimenter on another side of the planet can execute the same procedure at the same temperatures and pressures and get hopefully the same results. We needed a standard of comparison. And that's it, okay? So do yourself a favor, write the words, study the words, take the quiz, and move on. Thanks for watching. I'm going to click this here button, and I'm going to turn off this video. Oh, yeah.